Okay, now let's discuss some interesting behavior of Radamacher complexity. So the first thing is this. When we scale the hypothesis class, the scale also scale the Radamacher complexity. Okay, but to just a simple movement, the plus this vector a0 does not change the Radamacher complexity. Okay, so when you control the hypothesis by scaling factor, then your Radamacher complexity also proportionally scaled, but just simple movement. So for instance, your function calls this, but when you just simply move your function class, which does not change the Radamacher complexity. But when you scale this like this, then the scaling can change the Radamacher complexity. That is the Lemma 26.6. And the second thing that is very interesting, when you have some point, some vector that define your hypothesis class. So let's say this is A, some vector set of vectors. When you have this data point, the convex hull. So convex hull means the smallest convex set that includes the original set A. So A prime be the convex hull of A, and then the convex hull just simple linear combination among whole point in original set A. That is called convex hull. Okay, convex hull is the smallest convex set that include the original set A. So when you make a convex hull, the convex hull does not change the Radamacher complexity. We can keep the same same Radamacher complexity using the convex hull operation. Okay, so how can we have we can show the second property? That is very simple. So from the definition of Radamacher complexity and the convex hull, we have this. Okay. So for any integer n, let's consider n combination of original data point A, which means let's pick n point from original set A and then consider every possible combination, linear combination. So linear combination means let's consider some constant vector alpha of which L1 norm is sum of absolute values of each element of vector is equal to 1, and all the element of vector alpha is non-negative. Then alpha j aij, these represent a linear combination of vector a1 to a capital N. So this is our linear combination. And for this linear combination, we want to check the Radamacher complexity, and the Radamacher complexity is from the definition consider random sigma vector which either +1 or -1 for each element, the IID. Okay, so that is just a definition of Radamacher complexity for the n-point linear combination, and for any n-point linear combination, we have this simple trick. In the end we have this, and this thing just Radamacher complexity of original set A. Okay, linear combination does not change the Radamacher complexity. That comes from the definition of Radamacher complexity, and which can be very easily shown like this. Just use supremum and product simple property. Okay. Massart lemma is important thing that explains some property of Radamacher complexity as the training sample increase. Okay, so let A is our hypothesis set consists of capital N different functions. Okay, in M, so M dimensional space, which means for M training data point, each vector defines the output. Okay, or each vector defines the value, rows value for the corresponding training data point. Okay, so each AI vector m dimensional, right? And each element represents a rows value. Okay. And for this capital N vector represent each vectors represent corresponding rows value. Okay, for each hypothesis. So in this case, we have capital N number of different hypotheses on M training data point. So let's define A bar is kind of empirical mean among whole hypotheses. Then Radamacher complexity of this A, this is also bounded by maximum, so this is L to this norm of A minus A bar times square root 2 times log capital N over M. So as the training data point increase, as the number of training data point increase, we have smaller Radamacher complexity. So when M go to infinity, basically the Radamacher complexity is 0. That converts to 0. When we have bounded rows the vector, and we also have always some finite number of hypotheses. Okay, but note that when we have bounded rows value for each training data point, as the number of data point increase, as M increases, this value also increase, right? Imagine we have vector with finite interval values. Then the norm of this vector is proportional to, so let's say each element is bounded by C, the absolute value of each element is bounded by some C. The norm vector of this is bounded by C times square root 2 M. Okay, so this radius is not constant, which depend on the training number of training point. But one good news is usually this radius is proportional to square root M, and in the denominator we have M. So even if this value, this radius proportional to square root M, in total the Radamacher complexity will proportional to 1 over square root 2 M. That is good news, and that looks quite good, right? And another thing we have to consider is usually the hypothesis class size also increase as the number of training data point increase. Okay. right? So that also we have to be very carefully check. For instance, when we have VC dimension D, what is n? When we have VC dimension D, then this n value is roughly upper bounded by m power to d, m to the d. So this log n is upper bounded by d times log m. Again, good news is log is very slowly increasing function, so square root m much faster than log m. So we can almost ignore the log m term in the numerator. That is good news. So roughly the Radamacher complexity just proportional to square root to d log n over square root m, log m square root to m. Okay. So yeah, when we know BC dimension, Radamacher complexity is bounded by this vector, and that is reasonably good. Okay, so how to show the Massart lemma? So again, we will use the very nice result of this Radamacher complexity. So without loss of generality, we can assume that the empirical average of a vector is equal to 0 because this simple movement, simple addition to our hypothesis, vector addition to our hypothesis class does not change the Radamacher complexity. We can simply set a bar equal to 0. That is fine. And let's define a prime hypothesis class or a prime set is equal to just simply scaling of original set A. So this is not changed our theorem too much because we know that the scaling of hypothesis class or set just scaling as much as the lambda factor when we come to Radamacher complexity. That we know from the previous Radamacher complexity properties. So from this fact, let's study the Radamacher complexity of A prime. Then from the Radamacher complexity of A prime, we can easily understand Radamacher complexity of original A. Okay, and these two equality just comes from the definition of Radamacher complexity and just a simple trick. Log and exponential is just a linear function, and the max, we can simply upper bound the max using the summation. That is very useful trick, and I strongly recommend to remember this simple trick because we use this simple trick many places. Max can be easily upper bounded by summation because one of the element is the max. Of course, when this part is non-negative. Summation always increase the value, and among A prime, at least one point has the same value with the max of exponential inner product between sigma A. So we can upper bound this. Okay, so when we have non-negative values and when we take max of non-negative values, we can simply upper bound the max of non-negative values by summation of non-negative values. Alright, and then by Jensen's inequality, we can put the expectation inside log function with this inequality sign, and this is equal to this because each sigma I is independent, right? And we use some simple trick. I encourage you to check the book for the detailed proof. Here we use this trick: exponential a plus exponential minus a is bounded by exponential a squared over 2. Okay, using this inequality, we have this, and in the end, we have this. So again, the summation of the negative value is upper bounded by the cardinality of max. Okay, so that is very, it looks like very loose because here we upper bound max by summation, and here we upper bound summation by cardinality times max. So we, using this process, basically we multiply the cardinality of a to this max value. Okay, so it looks very loose, but when this part is very huge, log of this part plus log of this cardinality does not increase too much by this log of cardinality vector when this value is very huge. Then this simple tricks does not make too loose bounds. Okay, that is the key trick to show Massart lemma, and for the proof we use very important trick: max always bounded by summation, and summation always bounded by cardinality times max. It looks very stupid but very powerful, and many proofs utilize this trick. And then in the last step, we optimize lambda. Okay, and the lambda is optimized at this point. And so when you put lambda with this value, we can conclude this lemma.